A speedboat has got a mass of 580 kilograms, and it is equipped with an engine that is 3,000 watts, and the boat is traveling across a dam at a constant speed. At this speed, the engine is delivering 2,600 watts. Determine the efficiency, and the efficiency is 2,600 over 3,000, the maximum available, and we get a percentage, and it turns out to be 86.67%. Convert 65 kilometers per hour into meters per second, so it's 65 kilometers per 1 hour is equivalent to 65,000 meters divided by 3,600 seconds. And when I punch that into my calculator, I land up with 18.06 meters per second. Calculate the force that the engine is exerting on the speedboat while it is traveling at that speed. Power is equal to force times velocity. I know the power is 2,600, that's the output power. I know the velocity is 18.06, and therefore I can work out the force, and the force turns out to be 143.96 newtons. The pilot of the boat cuts the engine and the boat glides to a stop. State the work energy theorem. That is pure bookwork, and it's going to be the work done by a net force on a body is equal to the change in kinetic energy of that body, and hence calculate the work done by the average resultant force in bringing the boat to rest. So I'm going to say work done is change in kinetic energy, and we need to get that body to come to rest, so it's a half m v squared minus u squared, and that is equal to a half mass 58, and we're going to come to a halt, so it's 18.06 squared, and when I solve that all, I get 94,587.7, at least 44 joules. You could have done it in 2 steps, that would have been fine. De Bourgeois has a mass of 94 kilograms on Earth. He goes on a space mission to the moon. On the moon, he finds that he has a weight of 158 newtons, and the mass of the moon is given over there. So calculate the gravitational acceleration on the moon. Fg is always equal to mass times gravitational acceleration. That is, he's got a weight of 158, and his mass is 94, and therefore G turns out to be equal to 1.68 meters per second squared, and don't forget about the downwards or the down. Then you're going to use G in 6.1, or sorry, that should have been 8.1, to calculate the radius of the moon, and you are going to first say that you've got G is equal to G mass of a planet, radius of a planet squared. I've got 1.68, I've got 6.67 times 10 to the negative 11. I've got the mass of the moon is 7.4 times 10 to the 22, and when I divide that with r squared, don't forget to square root at the end, and your r turns out to be 1.71 times 10 to the 6 meters. State Newton's universal law of gravitation. So that is just bookwork. Any two objects in the universe attract one another with a force that is directly proportional to the product of their masses and inversely proportional to the distance between their centers squared. In NASA, there's a display case. 2 silver-covered balls are suspended as shown. Each ball has a mass of 4 kilograms. They are mounted so that their centers are exactly 1 meter apart. What is the gravitational force of attraction? This is a real level 2 kind of question. And it's G m1 m2 over r squared, and we land up with 6.67 times 10 to the negative 11. Their masses are 4, square both of those because it's 4 times 4, 1 squared because it's the radius squared, and I get 1.07 times 10 to the negative 9 newtons. What charge of equal magnitude should be placed on each ball so that the electrostatic force of repulsion exactly balances out the gravitational force of attraction? So we are going to say that F is equal to K Q1 Q2 over r squared. The force is the same as the gravitational one, but just in the opposite direction. And we now say 9 times 10 to the power of 9. The charges are, we do not know, but they are equal. So I can say whatever that charge is squared, q times q, not 2q, q squared. And the distance between them is still 1, and I have to square that. And what happens is the charge on each one turns out to be 3,44 times 10 to the negative 10 coulombs each. Now we've got Midyear. She sets up a circuit. The battery has an internal resistance of R and 12 meters, at least 12 volts on the voltmeter. Sorry, EMF of 12 volts. And V1 is 4. And calculate the resistance of the external circuit. So I can simply say 1 over 6 plus 1 over 6 is 1 over R parallel. And I land up with 2 over 6. And then I flip it, and R parallel turns out to be equal to 3 ohms. Not difficult. The external resistance is therefore going to be the 3 plus the 2. So this is an equivalent of 3, and I land up with 5 ohms. Calculate the reading on the ammeter. The reading on the ammeter, it's the same at all points of a series circuit, so I can use this resistor over here, and I can say I is equal to V over R, 4 over 2, and I get 2 amps. Calculate the internal resistance of the battery. So what I'm going to need to do now is I'm going to have to say, well, what is the total resistance of the entire circuit? So R total is equal to the EMF divided by the series current, and that is going to be 12 divided by 2, which is equal to 6 ohms. 5 of those ohms come from outside, so the internal resistance is 6 minus 5, which is 1 ohm. In the photo, the mixer and the microwave and the iron are connected to the same multiplug. Below is the circuit diagram of them, and we can work out the current on each, calculate the resistance of the mixer. So looking at just the mixer, I go power is equal to V squared over R. I choose that equation because I've got power and I've got potential difference, and I'm looking for resistance. So I go 220 is equal to, sorry, I lie, 440 is equal to 220 squared divided by R, and R turns out to be equal to 110 ohms. I can work out the current on that one. So current is equal to power divided by potential difference, so it turns out to be 2 amps. Power divided by potential difference, I go 1,320 watts divided by 220, and I find it's 6 amps on that branch, and I've got 4 amps on that branch. When I now add all 3 branches together, I get 2 plus 6 plus 4, and I get 12 amps. I need to very clearly say, will the circuit be able to run? 12 amps is less than 15 amps, which is what it can't exceed, and therefore it will be able to run. The iron is used for an average of 2 hours per day. And what is the cost? If the cost of electricity is given to me in cents, give the answer in rands. So the first thing I'm going to do is I'm going to say that my iron over here, I need to first work out its power. So power is equal to V times I, which is equal to 220, times 4, which is equal to 880 watts. If I'm looking for cost, I need kilowatt hours, and that is equal to 0.88 kilowatts multiplied by 2 hours each day, and I land up with an answer of 1,76 kilowatt hours. Nope, not per hour, just hours. And then I need to say multiply that by the cost. So the cost turns out to be 1,76 multiplied by 116,63, and that comes out to be approximately 205 cents, which in rands is R2.05. We've got a coil of wire over here. It's got 20 coils on it and an iron ring. The current is 6 amps, and that causes a magnetic flux as it gets turned on, I suppose. A second coil of 800 turns is now placed on the ring with the first coil. Calculate the current through those 800 turns. You are expected to know number of turns in primary. Current in primary is number of turns in secondary. Current in secondary is just a ratio. Substitute in 20 and 6 is equal to 800 times something or other. And something or other, the current in the secondary turns out to be 0.15 amps. So I've reduced the current. State Faraday's law of electromagnetic induction. Right, that's bookwork, and it's the EMF induced is directly proportional to the rate of change of magnetic flux. When the current in the first coil is a constant 6 amp, there's no EMF induced in the second coil. Why? Because we have to have alternating current. In order to induce a current, I must have a change in magnetic flux, and a constant 6 amps is not changing and therefore will not induce a current. What is this the system of? It is used in transformers. Now we have got this motor over here. It is, I lie, it says it's a DC generator, which it is, which looks a lot like a motor because a DC generator has got this split ring situation over here. Remember, an AC generator would have a slip ring. Anyway, the graph is the output potential difference, and as you can see, it does increase and decrease, but it keeps coming out in the same direction. State two ways in which the output of this generator could be increased. I could increase the strength of the magnets. I could spin this a little bit faster. I could put more wire onto that coil. I can't put any more current in because I'm trying to get current out, so that can't be one of your answers. Name and state the law that is used to determine the direction of the induced EMF. The law is known as Lenz's law, and it says that an induced current flows in a direction so as to oppose the inducing action. In which direction will the current flow in the coil in the above diagram? Answer either A, B. Now we have to work this out. You need your right hand, and you're going to take your first finger and point it from north to south. I'm going to worry about just this branch over here, and it's clearly going upwards. So I am going to put my thumb upwards, and then I am going to take a look at which direction the current flows in. And what I see is that it comes down the page. That means that this one would be going up the page, and therefore my current flow would be A, B, C, D. In other words, in like a clockwise motion. What type of graph, X or Y, corresponds to the coil in the horizontal, what time on the graph corresponds to the coil in the horizontal position as shown? Briefly explain your answer. At the point X, we have got maximum current because that's where the maximum cutting of field lines is occurring. Y is when we would be in the vertical position. So X, due to the greatest change in flux, the coil is cutting the field lines at 90 degrees at that point. State a change that you could make to a DC generator in order to get this situation. Well, this is obviously an AC generator giving me alternating current in both directions. What would I need to do? I would need to change that split ring into a slip ring. So split ring into slip ring. The above graph is reproduced on your answer sheet. Use the same set of axes to sketch the graph output potential difference that would be obtained if the new generator rotated at twice the speed. Now, if it rotated at twice the speed, what would happen, all that, is that we would definitely get twice the potential difference being induced, or at least a much bigger potential difference. The other thing that we would see is that we would be changing direction more frequently, so up and down again before we go again. So in other words, we would have a much, much shorter period. This obviously isn't the neatest diagram. That should be a straight line. That should be a straight line. So you more or less want to increase the peak, but possibly double it, and you definitely want to get double the number of waves in the same space of time because you are spinning it and therefore cutting the magnetic field lines twice as often and changing direction twice as often.